Okay, I want you to imagine for a second, before we get into the kNN algorithm, that you're seated at a restaurant and you're blindfolded, and you take a bite out of something that you don't know what you're eating. What is the immediate thing that comes to your mind when you bite into something and it's sweet and it's crunchy? Your mind automatically associates that thought with memories that you have of a fruit. So like an apple, perhaps. Basically, the kNN algorithm works in a similar way. You have unclassified data, and what you want to do is classify that data based on data that you currently have and find the distance between the nearest neighbor and the new point of unclassified data that you have. In this way, at the end of this chapter, we'll be able to figure out, based on the features of breast tissue tumors, whether they are benign or malignant, from a training set of data, and then we're going to test that training set to see how well it predicts classification of new tumors and whether they're benign or malignant. So, from what you can see here, we're going to do an example. So we've put ingredients like apples, bacon, bananas, carrots, celery, cheese, and we've ranked them from 1 to 10 in terms of sweetness and their crunchiness. And we know their food type as well. So we can classify an apple as a fruit, bacon as a protein, banana as a fruit, etc. What we can do from here is we can actually graph. So let's say this is sweetness versus crunchiness, right? And then we can see where certain things would lie. So let's say 9's about here and 10's about here, so we could probably find an apple around here. And doing the same for all of these, we'll get something like this. Now, as you can see, the apple is right there. We need to ensure that any dimension, so this is a two-dimensional grid, has the same order of magnitude. So this goes from 1 to 10, and this goes from 1 to 10 as well. This will be important, and I'll show you how to normalize later on. But as you can see, just based off this alone, we can see that things group together naturally. So these are all fruits. And right here, these are veggies. And here we have proteins. So the way the nearest neighbor classification works is, say we have a new data point somewhere here. Let's say it's a tomato. What is it? Is it a vegetable, a fruit, or a protein? Maybe don't even think of this as a tomato. Maybe think of it as you're blind and you just tasted something. And based off your previous knowledge, you have to classify where that is. We're going to be using the nearest neighbor algorithm for that. But first we have to understand something about Euclidean distance.
Alright, so for the
distance is given by the formula distance function of q and r. So let's say this is point q and this green bean is point r, is equal to the root of q1 minus r1 squared plus q2 minus r2 squared dot 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 all the way to whatever the last feature is. So say this went on and there was n-dimensional features. Qn minus Rn squared. Alright, so we have two features here. How about we calculate what the distance is? So the distance of a tomato to a green bean. Okay, so to the power of a half. And what we can do here is we can take 6 less 3 squared plus 7 less 4 squared. So this will give us an answer of 4.2. So this is the tomato to the green bean has a distance of 4.2. So let's use the simplest kNN example. K is the number of nearest neighbors that contribute to the classification. And we'll discuss bias-variance trade-off shortly in terms of what K to use. But let's start off with 1 NN. So what you have to do for a 1 NN is calculate all of the distances of the nearest neighbors, and whatever is the closest one, this is what the 1 means, the tomato will belong to that classification.
Alright, so here's a table of a summarized table of the distances associated with the tomato to all of these other fruits. So here we have grape, green bean, nuts, and orange. Since we're using 1 NN, we're going to find the lowest distance. So the lowest distance here is the orange. So under a 1 NN, a tomato would be classified as a fruit. Now let's say we used instead a higher K value. So how would we do that? Well, it just changes the weighting. You still have to calculate all the distances. Let's use 3 NN. Now we will take the 3 nearest neighbors. So that'll include the fruit. Who is the second nearest neighbor? The second nearest neighbor is the grape. And the third nearest neighbor is nuts, and that's a protein. Now, the way you would decide in the 3NN system is each of these casts a vote. How you want to do that, whether you want to do a weighted average or whether you want to do it as just a classification method, is up to you. But let's just say, for simplicity's sake, that 2 out of the 3 nearest neighbors classify the tomato as a fruit, therefore the tomato is a fruit. Alright, now we'll discuss bias-variance trade-off and what is the proper k-value used for your data set that you're analyzing. So let's discuss the bias-variance trade-off.
We have to keep in mind, with machine learning models, it's not about fitting perfectly to the data set. There's a lot of noise in a data set, and outliers will, if you fit to these outliers, you're contributing to overfitting. So let me give you an example that I think might be able to illustrate this. So say you have a set of data like this. It seems pretty linear, but say then you have like one data point that goes down here. If your model perfectly fits this data point and doesn't consider it noise or an outlier, it won't be able to predict the so this would be the training set. It wouldn't be able to predict a test set later on, because the test set is likely to follow the same linear relationship here, whereas it will predict values somewhere along here. So what you have to do is be able to have accurate predictions, and this is where you get into the bias-variance trade-off. So essentially there's 4 scenarios that you can have with a model. Say this is a target and this is the bullseye. And you want to hit the bullseye. So you can have accuracy. So you hit the bullseye around the bullseye. This is accurate but not precise. You can have precision, so very close clusters, but they're not accurate. Obviously, you can have the one where it's not accurate or precise. That would be the worst of the situations. Or you can have something, and this would be the ideal scenario, accurate and precise. So what k-value gives you accurate and precise measurements? So let's examine what k-values do. If you have a large k-value, you're gonna get accurate results, but not necessarily precise ones. You see, with a smaller k-value, you can actually fit around this noisy data, but that doesn't just if one of these things is misclassified, if this is actually a triangle, what you have is a model that might not work for the test set that you actually want. So a small k-value might not be feasible. Also, with a large k-value, you can be accurate, but so off the mark in terms of your precision, and that's not good either. So a typical rule of thumb is, say you have 15 observations, okay, let's say 16 observations, you want to use the root of 16 as your k-value. So that's going to be 4. So you're going to use a 4 NN model. A better way of doing this is to test various k models, so from 1 through 16. You can probably, through deduction, eliminate most of these and start testing around this region to see what actually gives you the best model. And it's a bit of more of an art than a science in that case. Alright, now we're going to begin actually working with a data set.
Actually, before we begin working with
the breast cancer data set, let's talk about normalization for a bit. So let's say in the example that we used, crunchiness and sweetness were on a 1 to 10 scale, and they were both on a 1 to 10 scale, so that was good. With a nearest neighbor problem, you don't want you want normalization of these values because you don't want a distance too high or too low just because the numbers are used on a different scale. So let me give you an example. Let's say we wanted to do 3 dimensions. So let's say, okay, sorry, 1 second. So say this is sweetness, this is crunchiness, and these range from 1 to 10. And then we have heat, which goes from 1 to 10 to the power of 10. As you can see, this is not an accurate representation because these distances are barely going to contribute to the a data point somewhere here. But under a normalization, if this 10 to the power of 10 was just 10, then it would be an adequate descriptor of what's actually going on. So let's talk about how to actually normalize. There's 2 methods, and it depends on the distribution of your data. So let's say we're using heat. Let's say the foods that you're classifying are of a uniform distribution. So there's an equal amount of not hot food, and there's an equal amount of really hot food. You can use this equation here, which takes a value, subtracts the minimum, and then you take the maximum, subtract the minimum, and then you get your new x value. And this will normalize this to a 1 to 10 scale. Now, let's say it was different. Let's say you had 0 and 10 to the power of 10, but you had a normal distribution. When you normalize to 1 to 10, you want to still account for the fact that most of the data lies in this central region here. So what you're going to want to use for normalization is this equation here, which is the x minus the mean over the standard deviation, and that'll give you your new x value, and that'll normalize it from 1 to 10 as well. Now we're going to go into the breast cancer biopsy data, and we're actually going to be doing normalization with that as well, so you can see that in practice.